All right, this is Unit 14, Day 3, Probability Day 3. Take a look at this warm-up here. Maybe pause the video for a second so you can read it and give it a shot. And when you're ready to go through it, hit play, and we'll see how you did. So go ahead. All right, so assuming that you've done it and you paused it, now you're ready to see the answers. Here we go. When a car is brought to a repair shop for service, the probability that we'll need a transmission fluid replaced is 0.38. The probability that we'll need brake pads replaced is 0.28. And the probability that it will need both the transmission fluid and the brake pads replaced is 0.16. Let the event that the car needs the transmission fluid replaced be T, and the event that a car needs the brake pads replaced be B. Okay. This is a good question to do as a Venn diagram because you've got overlap. You've got transmission fluid, you've got brake pads, and you've got some that need both. So that's kind of how you know that Venn diagram might be the way to go. Let's start by making a Venn diagram. And we'll call this T, that's transmission, and brake pads, we'll call that B over here. Remember, what do you want to always plug in first? If you know the overlap, 0.16, that's the first place you can start. So this is 0.16 in the center there. The trick is, like we talked about yesterday, if it needs the transmission fluid replaced, that means this entire T circle has to equal 0.38. We've already got 0.16 here. So if I do 0.38 minus 0.16, I'm going to be left with 0.22 for this part of the circle. Okay, similarly, for the brake pads, we got the brake pads replaced as 0.28. So to figure out what goes in this part of the circle, you got to take that 0.28, subtract off that 0.16, we're left with 0.12. So this part of the circle is 0.12. And then finally, remember, there's always something to put on the outside completely. The whole thing has to add to 1. So if I do 1 minus 0.22 minus 0.16 minus 0.12, we're left with what's on the outside, which in this case comes out to be 0.5. We got 0.5 out here. All right, so now we're ready to answer these questions. Probability that they need the transmission fluid replaced. That's the probability that you're inside this T circle. And I already told you that. That's 0.38, 0.22, and the 0.16. So this we could have gotten just by reading the question. We didn't actually need the Venn diagram for that part. Probability of the brake pads replaced. Again, they gave that to you. That's 0.28. Or if you look inside the entire B circle, 0.12 plus 0.16, it's going to give you that 0.28 that you need. Now remember, what does that symbol mean? Well, essentially it means intersection. Remember, it kind of looks like an A for and, like I said yesterday in class. So probability that you're having T and B at the same time. Intersection means overlap. That you can also get right from the work, 0.16. Don't even really need a Venn diagram. And the last thing is what we do need the Venn diagram for. Probability that you don't need transmission fluid or brake pads. Remember that C means complement. That means we don't want it, or not transmission or brake pads. So it's everything that's not in either circle, which is that thing on the outside of our Venn diagram, which is 0.5 up 0. All right, so today we're going to talk about something called the addition rule. We're going to come back to some of this question from the warm-up in a second and see how that relates to it. So this is the note sheet you should have. If you have a copy of it, print it out. There's a blank copy on my website as well as a filled-in copy. But I would try the blank copy and fill it in as I'm going, and it's just like you're sitting in class. It could be better. All right, so the addition rule of probability. Let's just talk about what the rule is first. If I've got the probability of A or B happening, turns out the rule is I got to take the probability of A happening plus the probability of B happening. But then I have to subtract off the probability of them both happening together. So probability of A and B. Another way to write that using our union and intersection symbols would be the probability of A or union B is equal to the probability of A plus the probability of B minus the probability of A and or intersect B. So the second row is kind of in math terms how we think of the addition rule. All right, so it says, let's see why this rule works. Given the Venn diagram shown, define P, Q, and R. All right, so I've got P is this piece of the Venn diagram, Q is this middle section, and R is this other section over here. So if I wanted to find the probability of A right now, that's the probability of anything inside that circle. So the probability of anything inside that circle would be P plus Q. If I wanted to find the probability of B right now, that would be the probability of anything inside this circle. If I wanted to do anything inside that circle, that'd be Q plus R. If I wanted to find the probability that I'm in both, so A intersect B, the part they have in common, that's just Q, that middle section. And lastly, if I want to do the probability of A or union B, that means anything that's in either of the two sections. And that's all three of them, P plus Q plus R. Those ideas are just stuff that we've done with Venn diagrams the last couple days. So that's nothing new. But let's look at this second definition that I did, the addition rule. It's kind of a proof of the addition rule. I've got the probability of A, U, B, A union B. I'm claiming that equals the probability of A plus the probability of B minus the probability of A intersect B. Now, based off of this Venn diagram I've got drawn over here, and all of these values I've already calculated, just knowing stuff about Venn diagrams, we can plug in this stuff for what we have written here. Probability of A union B, right over here, P plus Q plus R. That's what it should equal. Let's try this side. Probability of A is P plus Q. So this is P plus Q. Probability of B is Q plus R. So this is Q plus R. Minus the probability of A intersection of B, just minus Q. If I combine like terms here, I've got P plus 2 Qs plus R minus Q. Combine 2Q minus Q, and I get P plus Q plus R, which is what I said the probability of A union B should equal. So we've got what we expected, and that's why it works. So you can see why we need to subtract off this probability of A intersect B. That might be the piece that seems weird here. So most people think if I've got the probability of A or B, add the probability of A and B's together. But if you do that, you're potentially adding this middle section here twice, because that middle section is included in the probability of A and is included in the probability of B. And I don't need to include it twice, I only need to include it once. So this piece right here, I'm just going to write, we subtract the probability of A intersection B, so we don't count Q twice. All right, so now let's go back to that warm-up question for a second. So that warm-up question that we did a second ago with the cars and the transmission fluid. When a car is brought to a repair shop for service, the probability that it will need the transmission fluid replaced is 0.38. The probability that it will need the brake pads replaced is 0.28. And the probability that it will need both the transmission fluid and the brake pads replaced is 0.16. Remember, T is talking about transmission fluid, B is talking about brake pads. I want to find the probability that a randomly selected car needs the transmission fluid or brake pads replaced. Remember, as soon as you see or, think of that union. So we're looking for the probability of T or B. And in the warm-up, we made a Venn diagram. I'm just going to copy that here quick. So the Venn diagram, we had T, and we had B, and we had that 0.22 was here, 0.16 was in the middle, and 0.12 was over here, with 0.5 on the outside. Not going over all that because we just calculated that with the warm-up. So if I want the probability that I'm in either circle, T or B, from the Venn diagram, we've said before we could just do 0.22 plus 0.16 plus 0.12. And if I have a Venn diagram to look at, I can see that that's equal to 0.5, so my probability is 0.5. Or consider not using a Venn diagram. We could use that addition rule that we just learned to say that the probability of T or B is equal to the probability of T plus the probability of B minus the probability of T and B. So if I try not even to look at this Venn diagram for a second, so don't even look at that, we know the probability of T, transmission fluid, is 0.38. We know the probability of B, brake pads, is 0.28. We know the probability that it needs both is 0.16. If I do 0.38 plus 0.28 minus 0.16, look at what I get. 0.5. So I got that answer that we got from the Venn diagram without even using the Venn diagram. And sometimes it's a little bit easier. Since the setup gave me all the information that I needed, it was a lot faster for me to just plug into this formula and figure out what all the pieces of the Venn diagram meant. Okay, let's go on to the next question. Next page. Here we go. A small high school surveyed 52 of its seniors about their plans after they graduate. They found the following data and wanted to analyze it based on gender. In this case, if we pick a student at random, we can place them into one of four events. M is male, F is female, C means going to college, N means not going to college. And they've got totals of all the people who responded to their survey over here in this chart. Part A just wants you to give the values for each of the following. So when you see N, this means the number of, as opposed to probability of. So NM just means the number of males. If we want to look at the male column here and look at the total number of males is 30. NF would be number of females. So look at the female column over here. Total number of females is 22. Number going to college. Find your going to college row. Look at the total, 29. Number not going to college. Not going to college row, total's 23. Two gets a little trickier. Number of M and C, meaning they have to be in the male column and the going to column row. So male and going to college, there's the overlap, it's 16. Female and going to college. Find your female, crisscross it with going to college. We got 13 of those. How about female or college? Now this is where what we're talking about today comes in. Female is everything in this column. So we got 13 people here and 9 people there. or going to college. Well, going to college is everything in this row. But if I say 16 of those and 13 of those, what have I just done? Well, I've counted 13 twice. I don't want to do that. So it's not as easy as just saying 22 plus 29. There's an overlap. There's 16 plus 13 plus 9. So I can either just count those up, kind of like I'm counting the circles in the Venn diagram, or I could use the addition property and say, I could say number of F or C would be the number of females plus the number going to college minus the number of females who are also going to college. That was that section we counted twice right here. So number of females, 22, plus number going to college, 29, minus the number of females who are also going to college, is 13. It gives us a total of 38. And just verify real quick, that's the same as saying the females, so those 13 plus 9, plus the extras who are going to college who aren't female, the 16 males. Add those together, you also come up with 38. All right, part B, now we're going to talk about probabilities. What's the probability that a person picked at random would be a female who is going to college? Represent this using either a union or an intersection. So they are a female. You say or they're going to college, or and they're going to college. It's and. So and means intersection. It's probability of female and intersect college. That's easy. I just look at the table, female going to college. This probability now, it's 13 out of the total of responders are down here in the corner, 52. So 13 out of 52 reduces to 1 out of 4. Part C. What's the probability that a person picked at random would be a female or someone going to college? Now this is probability F union C. That's tricky. You could take your 38 number from right above and say it's 38 out of a total of 52, which comes out to be 19 out of 26. That's our final answer. These last two questions talk again about that addition rule. Explain why probability of F or C is not equal to the probability of F plus the probability of C. Well, we know the probability of F or C is 19 out of 26. If I try to do the probability of F, the probability that you're a female is 22 out of those 52. Plus the probability that you're going to college is 29 people out of that 52. If you check real quick, 22 out of 52 plus 29 out of 52, math frac, 51 out of 52. That's not 19 out of 26. So it doesn't work, and the reason is that each of these included females who go to college. So we counted that females going to college twice. So this general probability law that's based on this idea, again, is that we should have done the probability of females or college is equal to probability of females plus probability of college minus the probability of females and went to college. So then we get 22 out of 52 plus 29 out of 52 minus this number from up here, 13 out of 52. And if you add those all up, 22 plus 29 minus 13, it comes out to be 38 out of 52, which is that 19 out of 26 we got above. So just another illustration of why you've got to use the addition rule. Okay. Now there are some times when it seems like we're not subtracting off, or that we don't need to subtract off this intersection. That's what this next thing says. Well, let me read this first. Sometimes we can avoid the probability law that we encounter in E by simply keeping careful track of what elements of the sample space are in both of our sets and making sure we don't count them twice. That's essentially what we did when I was showing you that this row and this row both counted as 13 twice. So if I wanted to figure out how many females or went to college, I would add up all the females and the remaining people that went to college, not counting that 13 twice. That's what this is saying, but that's a little tricky to do sometimes. So it's better to use this formula. All right. But there's always this extra piece, mutually exclusive. And that means when there are no outcomes in common. So essentially, if I'm looking at a Venn diagram and I've got A and B, there's no overlap. A and B are totally separate. Okay? And we say the probability of A and B happening at the same time is 0. So like, for example, if I said, what's the probability that it's Monday or Tuesday? Well, that'd be 2 days out of 7. But the probability that it's Monday and Tuesday at the same time, that's 0. They're mutually exclusive. All right, so this next question deals with mutually exclusive. On a certain midterm exam, there were 7 A's, 12 B's, 3 C's, and 1 F. Determine each of the probabilities. If I were to make a Venn diagram of this situation, we'd have 4 circles. But none of them are overlapping. Because you either have an A, or you have a B, or you have a C, or you have an F. There's 7 of these, 12 of these, 3 of these, 1 of those. The probability that you got the F, unfortunately, is 1 out of, how many total people are there? 19, 20, 23. So 1 sad person out of 23. Probability that you got an A and a B. You can't get an A and a B. You either got an A, a 90 to 100, or you got a B, an 80 to 89. So that's 0. And as soon as we know this, we can say A and B are mutually exclusive. Why? Well, you can't get an A and a B at the same time. However, it is possible to get A or B. Let's use the addition rule. Probability of A plus the probability of B minus the probability of A and B. The probability you get an A is 7 out of 23. Plus the probability you get a B is 12 out of 23. We just said the probability of getting an A and a B together is 0. So in the end, it comes out to be 19 out of 23. So in this case, I can just add the probability of A and the probability of B because there's no overlap. Okay, here's another or. Probability of B or not A. That's like saying the probability of B plus the probability of not A, which I can write as A complement, minus the probability of A and, probability of B and A complement. This one's a little trickier. Probability of B isn't too bad. That's 12 out of 23. What about the probability that you didn't get an A, not an A? Let's either B, C, or F. So 12, 15, 16. So 16 out of 23. But probability of B and not A is not mutually exclusive. Because if I look at the probability of B, that's obviously this. The probability of not A is all this other stuff. So there is some overlap there. So this time it does matter. What's the probability that I got a B and didn't get an A? Well, the overlap are those 12 people that got the Bs. So I have to subtract off 12 out of 23. And it comes out that my answer is 16 out of 23. Part E we already answered. Are A and B mutually exclusive? Why or why not? Answer that right here. They are mutually exclusive because you can't get A and B at the same time. All right. The rest of these kind of deal more with the addition rule as the formula. Here's 4. Insurance companies typically try to sell many different policies to the same customer. At the Flows Insurance Company, 56% of all the customers have their car insurance policies. 48% have home insurance policies, and 18% have both. Customers picked at random. Part A. Find the probability that he or she has at least one of those policies. So let's say probability that they have car insurance is 56%, 0.56. Probability that they have home insurance, we'll call that probability of H, is 0.48. Probability that they have both, that's car and home, intersection, is 0.18. So if I want at least one of the policies, that means the probability that they have car or home. And that'd be using the formula. Probability of car plus probability of home minus the probability of car and home. Probability of car is 0.56. Probability of home is 0.48. Minus the probability of both of them at the same time, minus 0.18. Comes out to be 0.86. So an 86% chance. Now, real quick, I could have done this with a Venn diagram also. If you prefer that way. I think it takes longer. Here's car, here's home. You have to fill in your overlap of 0.18. You have to take your 0.56, subtract off that 0.18 to get 0.38 in this circle. You have to take your 0.48, subtract off the 0.18 to get 0.3 in this circle. And if you add them all up, subtract from 1, you get the 0.14 left out here. So now if I'm looking for the probability that they have at least one of the policies, at least being the key, so maybe they have both, you can see that if I just do 0.38 plus 0.18 plus 0.3, you also get 0.86. It's doing the same thing, but you're keeping track of not counting that overlap twice. Part B, find the probability that he or she has neither of the policies. Well, if you think about it, isn't that exactly the opposite of what I asked in Part A? You either have at least one, and if you don't have at least one, that means you have none. So this is essentially the probability of C union H complement. Remember how I found complements? I either look outside, 0.14, or if I have the probability of it definitely happening, then not happening is just 1 minus 0.86, which is where that 0.14 comes from. All right, almost done. 2 more. This one's quick. Given that the probability of A is 0.3 and the probability of B is 0.7, if A and B are mutually exclusive, then which of the following is a true statement? Remember, mutually exclusive. Here's A, Here's B. We got no overlap. A is 0.3 probability. B happening is 0.7. Would the probability of A or B happening equal 1.0? You can see in the Venn diagram, yes, it would. Or we could say probability of A plus probability of B minus probability of A intersect B. I'd have 0.3 plus 0.7. Since they're mutually exclusive, we know that this is 0. There's my 0.10. So 1's true. Probability of A and B happening equals 0.21. No, def not. We just said that they're mutually exclusive. That's supposed to equal 0. So that's wrong. So 3's wrong for the same reason. A and B happening are mutually exclusive. Def not going to happen. Probability of A or B equaling 0.21. We calculated it's 0.10. So that's wrong. Both 1 and 2 can't be true either. So it's definitely choice 1. All right, last page, last one. Oh, just kidding. There's 2 more, but they're short. There are 20 climbing ropes at Merritt climbing walls. 5 are thicker than 8 millimeters. 4 are waterproof, and 1 is both thicker than 8 millimeters and waterproof. What is the probability of a rope being thicker than 8 millimeters or waterproof? So we could use the Venn diagram, or let's just use the addition rule. So probability of, we'll say T is thicker, or, because or means union, we'll call W waterproof, should equal probability of T plus probability of W minus the probability of T and W. And this should be quick because we got everything we need. There's 20 ropes, 5 are thicker than 8. So probability that they're thicker is 5 out of 20. 4 are waterproof. So 4 out of the 20 probabilities are waterproof. And 1 is both thicker and waterproof. That's your intersection. So minus 1 out of 20. Well, this is kind of nice because they all have the same denominator. 5 plus 4 is 9. Minus 1 is 8 out of 20. Reducing that, divide them both by 4. You're left with a 2/5 chance. 2/5. We use the addition rule because they gave us everything we needed to know. All right. And the last one. The probability that Maggie has ice cream in a waffle cone is 0.4. The probability that she has it in a sugar cone is 0.5. What's the probability that her ice cream is in a waffle cone or a sugar cone? Seems like it doesn't give us enough information here. We have an or. So if I want the probability of waffle cone, W, or sugar cone, S, should equal the probability of waffle plus the probability of sugar minus the probability of waffle and sugar. We've got probability of waffle, that's 0.4. We've got the probability of sugar, which is 0.5. But they neglected to give me the probability that it's a waffle cone and a sugar cone. Why is that okay? Well, I don't think you can be a waffle cone and a sugar cone. You're either or. It's one or the other. So that probability would be 0. That means because waffle cones and sugar cones are mutually exclusive. Can't be both at the same time. I notice there's still a 0.1 probability left over. That just means she doesn't have a cone at all, probably. So when I get this, my answer is 0.9. So if they don't give you the intersection or the and scenario, it might just be because there's no way that can happen. They're mutually exclusive. So watch out for that mutually exclusive stuff coming up in problems as well. All right, that's it. So give the homework a shot, and there's another Green Book assignment with that. And Let me know if there's any questions. Good luck.